Hi, my name is Kaylee, and this is my submission for Lab 3. In this lab, I used a computational physics simulation written in GlowScript to analyze orbital motion. Part 1 focused on determining the mass of a black hole by analyzing the motion of a star orbiting it, and then Part 2 involved simulating a spaceship orbit influenced by both a planet and its moon without crashing. So the first part of the lab simulated a star orbiting a black hole located at the origin. The star's position data was generated from the GlowScript program using a seed that was generated from my email address, and then using the position data, I calculated velocity and acceleration and the net gravitational force on the star. And then the next slide will include a screenshot of that code. So here's the code for part 1. And then to estimate the black hole mass, I used Newton's law of universal gravitation. First, the simulation calculated the net force on the star using the change in momentum over time, and then I rearranged the gravitational force equation to solve for the black hole mass. And then the program calculated the black hole mass at each point in the star's trajectory. So because of the numerical variations during the simulation, the final result was determined by averaging the calculated values across the dataset. Here's the actual video from that. As you can see, all the numbers are on the bottom, and just averaging those gives us the about the mass of the black hole. And then for part 2, I simulated a spaceship orbiting in a system with both a planet and a moon. The moon moves in a circular orbit around the planet, and the spaceship starts above the moon's surface. The spaceship's motion is influenced by gravitational forces from both bodies. So here's all the code from part 2. It's also going to be a little hard to see, but that's all that was done. So after testing different initial velocities, I found a velocity that allowed the spaceship to move in a stable orbit influenced by both the moon and the planet without crashing. The trajectory forms a complex path rather than a simple circular orbit, or it's supposed to, but mine is pretty circular, a little bit oval, and here's the actual video for that as well. It started a little bit late. And I changed the delta t and the t max to get just a quicker graphing, and it goes on for a long time, so I did stop the video early. So what does that mean? Newton's second law states that the net force acting on an object equals the rate of change of its momentum. In the simulation, we don't directly measure the force. Instead, we observed how the star's velocity and momentum change over time. By calculating the change in momentum between the steps, we determine the net force acting on the star. The parallel component of the star changes the star's speed, while the perpendicular component changes its direction and keeps the star in orbit around the black hole. And then for what if, to fully model the motion of the system, the simulation would need to include gravitational interactions between every object. Each body exerts a gravitational force on every other body, which creates a complex problem. Some interactions are going to be more dominant because of larger differences in mass. An example of this is the forces of the black hole and the star versus just this force from the spaceship. So in practice, simulations definitely simplify the system by focusing on those stronger forces and interactions. And that's it. Thank you for listening to my presentation. See you next time.